Hey everyone, and welcome to this explainer. Today we're taking a rapid-fire journey straight into the foundations of matrices and determinants. And don't worry, we're completely bypassing all that dense textbook jargon to break down these complex formulas into clear, visual rules that, actually make sense.
Because really, think about it. How do we organize the absolute chaos of complex data in fields like computer graphics, physics, engineering, or even economics? I mean, we don't just guess, right? And we certainly aren't writing out endless lists by hand. We use matrices. Far from just being some boring math you have to memorize for a test, matrices are essentially the ultimate superhero tool of the mathematical world. They're literally the highly efficient, structural DNA of data organization that secretly powers so much of our modern technological world. Okay, let's dive into this. Here's our mental roadmap for today's explainer. First, a welcome to matrices. Second, matrix algebra basics. Third, decoding determinants. Fourth, the matrix inverse. And finally, solving linear equations. All right, section 1, welcome to matrices and how we organize data. So, to kick off our toolkit building session, what exactly is a matrix? Well, simply put, it's a rectangular arrangement of numbers or symbols, kind of like a perfectly structured, highly organized mathematical spreadsheet. Now, the spatial language here is incredibly important for you to visualize. We've got M rows, which are the lines running straight across horizontally, and we have N columns, which are the lines dropping straight down vertically. Together, these create what we call the order of the matrix, which is written simply as M by N. So try to picture this grid in your mind right now, because before we even start calculating anything, you just need to remember that a matrix is simply a spatial framework used to hold information. And we actually categorize these grids by their shape and what's inside them. So we have row and column matrices, which are exactly what they sound like, a matrix restricted to just one single row or one single column. Then there's the square matrix, which is perfectly balanced with an equal number of rows and columns. But take a look at the visual patterns in the zeros and ones as we move further down the list. A diagonal matrix clears out everything to zero except for a diagonal line of numbers. An identity matrix is a really special type of diagonal matrix with solid ones directly down the middle and zeros everywhere else. Then you have the null matrix, which is just an empty void of all zeros. And the transpose? Well, that's actually an action. It's when you take a matrix and literally flip it, turning its horizontal rows into its vertical columns. Establishing these visual rules right now is absolutely crucial.
Moving right along, Section 2, Matrix Algebra Basics. Let's talk about combining matrices. Now, when it comes to combining these grids, the rules vary wildly depending on what exactly you're trying to do. Addition and subtraction? Wonderfully simple and intuitive. You just add or subtract the numbers in their corresponding spots. But there's a catch. Both matrices must be the exact same order. So you can only add a 2x3 matrix to another 2x3 matrix. Makes sense, right? Multiplication, however, introduces much stricter rules of engagement. For matrix A to successfully multiply with matrix B, the number of columns in matrix A absolutely must equal the number of rows in matrix B. So when you multiply an M by N matrix with an N by P matrix, those inner N dimensions effectively cancel each other out, and your brand new resulting matrix takes the shape of the outer dimensions, which is M by P.
Listen, if there's one single thing you take away from matrix algebra today, let it be this. Order completely matters. Unlike regular numbers where, 2 times 3 is exactly the same as 3 times 2, in the matrix universe, A times B is generally not equal to B times A. It's kind of like a mathematical plot twist. The other properties, thankfully, are much more familiar. You can group multiplications together, which is associativity. You can distribute a matrix across an addition equation, and if you have scalar multiplication, meaning you just multiply a matrix by a single regular number, well, that scalar multiplies against every single element inside the grid.
Okay, section 3, decoding determinants. This is where we find the matrix soul.
Right, so here we're shifting gears from simply organizing blocks of numbers to actually extracting a matrix's hidden numerical value, which is called the determinant. So what is a determinant? It's basically a single numerical value that is associated exclusively with square matrices. If your matrix isn't perfectly square, it simply doesn't have a determinant, no exceptions. You can really think of it as the secret sauce that boils down the entirety of a complex grid into one definitive number. And for a simple 2x2 matrix, the formula is quite elegant. You just cross-multiply the diagonals and subtract them. So you take the top left element A, multiply it by the bottom right element D, and then subtract the top right B multiplied by the bottom left C. It is always A times D minus B times C. Let's look at how this actually plays out in practice. Using our source example, imagine a 2 by 2 square matrix where the top row is 2 and 4 and the bottom row is 3 and 5. Following our cross-multiplication rule, we take 2 times 5, which gives us 10. Then, we subtract the other diagonal, 3 times 4, which gives us 12. 10 minus 12 resolves cleanly to -2, and there it is. That -2 is our determinant. Pretty straightforward, right?
Now let's see how this builds into the 3 by 3 determinant shortcut formula. This is a multi-step expansion, so stick with me. To find this determinant, we expand using the top row. That's elements A, B, and C. Step 1. Take element A, mentally delete its entire row and column, and multiply A by the determinant of the mini 2 by 2 matrix left behind. That gives us A multiplied by the quantity E times I minus F times H. Now step 2 is where people always make mistakes. You must subtract the next part. Take element B, cross out its row and column, and multiply it by the leftover diagonal calculation, D times I minus F times G. Finally, step 3. We switch back to addition. Add element C times its corresponding mini-matrix, D times H minus E times G. It's just a continuous, alternating rhythmic pattern. Positive, negative, positive.
So you might be wondering, why do we even care about calculating this number? Well, because determinants have these amazing properties that essentially act like mathematical cheat codes. For instance, if you swap 2 rows in a matrix, the determinant just flips its sign. If you spot that 2 rows are perfectly identical, you don't even have to do the math. The determinant is instantly 0. And the determinant of any identity matrix is beautifully simple. It's always exactly 1. But even more fascinating, we can connect this back to real-world geometry. If you take the standard x-y coordinates of 3 points on a graph and plug them into a determinant formula, it will actually calculate the exact area of the triangle they form. And if that area equals 0, it proves those 3 points are perfectly collinear, meaning they sit exactly on a single straight line. How cool is that? Moving on to section 4, the matrix inverse. It's time to talk about undoing operations. To truly master matrices, we have to learn the absolute crucial skill of undoing operations. To find an inverse, we first need to calculate the adjoint of a matrix. Now, I know this sounds incredibly complex, but it's really just a systematic 3-step buildup based on things we already know. First, you calculate a minor for every single element, which you get by temporarily deleting that element's row and column. Next, you apply a specific alternating plus or minus sign change to those minors to create what's called a cofactor matrix. And finally, you just transpose that cofactor matrix, remembering our earlier rule of swapping horizontal rows into vertical columns. Once you do that transpose, boom, you found the adjoint. Once you have the adjoint in hand, you plug it right into this master inverse formula. A inverse equals 1 divided by the determinant of A multiplied by the adjoint of A. But be warned, the mathematical stakes here are pretty high. Remember that we're actively dividing by the determinant here. So if your determinant calculated out to 0, you're trying to divide by 0, which we all know is impossible. In matrix terminology, we call this a singular matrix, and its inverse absolutely does not exist. It's just a complete dead end.
Thankfully, if you're working with a 2 by 2 matrix, there's an incredibly fast shortcut to bypass all of that heavy cofactor lifting. Step 1. Calculate 1 divided by your determinant, which is that AD minus BC formula we learned earlier. Step 2, look at your matrix and physically swap the positions of the top left A and the bottom right D. Step 3, leave elements B and C where they are, but just change their signs. Make the positive negative and the negative positive. And that's it. You've just created the inverse matrix. Knowing this shortcut will save you massive amounts of time on exams, which links perfectly back to the SwetaxAI learning tip about focusing on systematic practice for these common calculations.
And finally, Section 5, solving linear equations using matrices, the final boss fight. Consider the stark contrast here. On one side, you have this messy, chaotic, towering stack of simultaneous algebraic equations. You've got x's, y's, and z's, all jumbled together with various coefficients and constants. But on the other side, by utilizing matrices, we magically transform all of that algebraic chaos into a single, clean, incredibly elegant line of logic. A times x equals b. Matrix A perfectly captures all your coefficients, matrix X holds your targeted unknown variables, and matrix B neatly files away all your constants. It is the absolute ultimate in data organization. So the ultimate question is, how do we find X? How do we unlock those hidden variables in a single swoop? Well, this is the grand reveal of matrix algebra. To isolate X, we simply take our constant matrix B and multiply it by the inverse of matrix A. That's literally it. X equals A inverse times B. By simply running that one single matrix multiplication, we instantly and flawlessly solve the entire massive system of equations all at once. No more endless, tedious algebraic substitution required. But hey, quick pro tip here, before you spend 10 minutes doing all that intense math to find the inverse, it's really good to know if a solution even physically exists in the first place. We can quickly analyze matrix ranks to figure this out. If the ranks of your matrices match up properly, you have what's called a consistent system, meaning there is at least one valid solution. If the ranks don't match, you're dealing with an inconsistent system, and there is mathematically no solution at all. It's a brilliant time-saving test to see if the system is even solvable before you step into the ring. Wow, okay, we've covered a ton of ground today, so let's do a rapid-fire revision of the absolute must-remember takeaways from our sources. First, matrix multiplication is generally non-commutative. A times B does not equal B times A. Second, a determinant of 0 guarantees you have a singular matrix with absolutely no inverse. And lastly, a vital whisper directly from the SwetaxAI learning tips. Practice these steps systematically and relentlessly focus on sign accuracy. Missing one single negative sign will entirely derail your determinant expansion. Attention to detail is everything here, folks. To wrap up today's explainer, I really want to leave you with this final perspective-shifting thought. Matrices aren't just abstract, disconnected textbook concepts drawn on a whiteboard. Think about the physical device you're watching this on right now. How many millions of simultaneous matrix calculations do you think your computer's graphics card just processed in the last second alone to rapidly transform, scale, and render the graphical visuals onto your screen? The invisible mathematical grids we explored today are constantly working behind the scenes, literally powering the visual and structural reality of your digital life. Thanks for joining me on this journey, and keep exploring.